Hello friends, the topic for today is 8051 interrupts. An interrupt is an external or internal event that interrupts the microcontroller to inform it that a device needs its services. 5 interrupts are provided in 8051. 3 of these are generated automatically by internal operations: timer flag 0, timer flag 1 and serial port interrupt RI and TI. 2 interrupts are triggered by external signals provided by circuitry that is connected to pins INT0 and INT1. In today's video, you will learn the 8051 interrupts and interrupt enable and interrupt priority registers of 8051. Let us start. Welcome to our channel Engineering and Technology for You. The topic for today is 8051 interrupts. Introduction. An interrupt is an internal or external event that interrupts the microcontroller to inform it that a device needs its service. Internal event interrupts are generated due to timer overflow or transmission reception of byte through the serial port. In case of external events, the status of the microcontroller pins is altered to interrupt the microcontroller. Here we will be using the INT0 and INT1 pin. Any interrupt can cause 8051 to perform a hardware call to an interrupt handling subroutine that is located at a predetermined absolute address in program memory. That is called as the interrupt vector. Then 5 interrupts are provided in 8051. 3 of these are generated automatically by the internal operations, that is timer flag 0, timer flag 1 and serial port interrupt RI and or TI. 2 interrupts are triggered by external signals provided by the circuitry that is connected to pins INT0 and INT1, that is port pins P3.2 and P3.3. All interrupts functions are under the control of program. The programmer is able to alter control bits in the interrupt enable register, the interrupt priority register IP and the timer control register TCON. Then let us see the interrupt enable IE register. It is a 8-bit register. These are the bits. Bit 7 is EA, bit 5 is ET2, bit 4 is ES, bit 3 is ET1, bit 2 is EX1, bit 1 is ET0 and bit 0 is EX0. So EA is nothing but enable interrupt bit. So it is cleared to 0 by program to disable all interrupts and set to 1 to permit individual interrupts to be enabled by their enable bits. So it is a global bit to enable or disable all the interrupts. Then this is not implemented and this is reserved for future use, ET2. Then ES is enable serial port interrupt set to 1 by program to enable serial port interrupt and clear to 0 to disable serial port interrupt. Then next is ET1, that is enable timer 1 overflow interrupt. Again it is set by program to enable timer 1 overflow interrupt and clear to 0 to disable the timer 1 overflow interrupt. Then next is EX1, that is enable external interrupt 1 set to 1 by program to enable INT1 interrupt. This is the pin on 8051 microcontroller. Then clear to 0 to disable INT1 interrupt. Then next is ET0, that is enable timer 0 overflow interrupt. Again for set to 1 to enable, and if it is 0 the will disable the timer 0 overflow interrupt. and last bit is EX0, that is enable external interrupt 0. So again set by program to enable INT 0 interrupt, then clear to 0 to disable INT 0 interrupt. So these are all these pins, they are bit addressable as IE.0 to IE.7. When we do the program for enabling the interrupt, at that time we will make use of this. Then let us go to the interrupt priority or IP register. Again it is a 8-bit register, so these 3 bits they are not used, this is for future use. And then we have the PS, that is priority of serial port interrupt. So it is set or cleared by the program. So here priority may be 1, that is it will have the highest priority, and 0 means lowest. So for all the bits the same thing will apply. So then this is for priority of timer 1 overflow interrupt, set or cleared by the program. Then PX1, priority of external interrupt 1, set or cleared by the program. Then next is PT0, priority of timer 0 overflow interrupt. And then next is PX0, priority of external interrupt 0, set or cleared by the program. So if you make it, set it to 1, it will have the highest priority. If you make it 0, it will have the lowest priority. And again these bits are also bit addressable, IP0 to IP7. So these 2 registers, IE and IP, are very important for the interrupts. Then next we'll see the different types of interrupts. First is internal interrupts. So we have the timer flag interrupt. When timer counter overflows, the corresponding timer flag TF0 or TF1 is set to 1. So that will interrupt the microcontroller. The flag is cleared to 0 when the resulting interrupt generates a program call to appropriate timer subroutine in memory. So as soon as the flag is set, it will generate the interrupt, and then it will be cleared to 0 when the resulting interrupt generates a program call to appropriate timer subroutine. Then next we have the serial port interrupt. If data byte is received, an interrupt bit RI is set to 1 in the SCON register. Similarly, when data byte has been transmitted, an interrupt bit TI is set in the SCON. These 2 bits are in the SCON register. These are all together to provide a single interrupt to the processor, the serial port interrupt. So combinedly, RI and TI, they are combined with the OR gate, and that will generate the serial port interrupt. The program that handles serial data combination must reset RI or TI to enable the next data communication operation. So that has to be done by the program for the serial data communication. Then we go to the external interrupts. So pins INT0 and INT1 are used by the external circuitry. Inputs on this pin can set the interrupt flags IE0 and IE1 in the TCON register to 1 by 2 different methods. So first method, IEX, here we are talking about IE0 or IE1, so we designate it as X. Flags may be set when the INT-X. So if we are considering IE0, then it will be INT0. Signal reaches a low level. So that is one way, and the flags may be set when high to low transition takes place on INT-X pin, INT0 or INT1 pin. So accordingly the flags IE0 or IE1, they are set or. So bits IT0 and IT1 in TCON program the INTX pins for low level interrupt when set to 0, and program the INTX pins for transition interrupt, that is whenever there is a transition from high to low, so that will when set to 1. So this is how we will be using the external interrupts. Then interrupt control. The program must be able at critical times to inhibit the action of some or all interrupts, so crucial operations can be finished. So that is, we should be able to mask the interrupts when there is an emergency at that time. So IE registers hold the programmable bits that can enable or disable all interrupts as a group, or if the group is enabled, each individual interrupt source can be enabled or disabled. Just now we have discussed the IE register details. So there is EA pin for the enabling and disabling as a group, and individually we have the different pins for each of the interrupt source. Then often it is desirable to be able to set priorities among the competing interrupts that may conceivably occur simultaneously. So whenever two or more interrupts occur at the same time, then we should have the priority. So IP register bits may be set by the program to assign priorities among the various interrupt sources, so that important interrupts can be serviced first whenever there are multiple occurrence of the interrupt. Then let us go to the interrupt priority. The register IP determine if any interrupt is to have a high or low priority. So bit set to 1 gives accompanying interrupt a high priority, while 0 assign a low priority. Interrupts with high priority can interrupt another interrupt with lower priority. The lower priority interrupt continues after the higher is finished. So if two of the same priority occur at the same time, then they have the following ranking. So these are the ranking. I0 is the highest priority. Then we have the TF0, timer flag 0. Then IE1, external interrupt, and then timer flag 1, and last is serial interrupt RI or TI. The serial interrupt, now you can see here it is having the lowest priority, could be given highest priority by setting the PS bit in IP to 1 and all others to 0. So that means we can change the priority of the interrupts with the help of these bits. So if you want to have highest priority for serial interrupt, then you set the PS bit to 1 and all other bits to 0. So automatically it will have the highest priority. Then interrupt destination vectors. Now each interrupt source causes the interrupt program to do some hardware call to one of the dedicated addresses in the program memory. It is the responsibility of the programmer to place a routine at the address that will service the interrupt. These memory locations are shown in the following table. So these are the interrupts. I0, the address is 0003H, hexadecimal address. Then TF0, it is 000B. IE1, it is 0013H. TF1, it is 001BH, and for serial interrupt the address is 0023H. So whenever we want to use these interrupts, we'll have to put the interrupt service routine at these locations. These are the locations where we'll have to place the routine so that we can service the interrupts. Then enabling and disabling an interrupt. See, upon reset, all interrupts are disabled. That is masked. So, meaning that none will be responded by the microcontroller if they are activated. then interrupts must be enabled by software in order to for the microcontroller to respond to them. There is a register called IE, that is interrupt enable register, that is responsible for enabling or disabling of the interrupts. We'll take example so that it is clear to you. Show the interrupts to enable the serial interrupt, timer 0 interrupt and external hardware interrupt 1. Let us see the A part. So for this, what we'll do, we have the bits. So according to the bits of the IE, the first bit will have to set to 1, because EA, that is for EA, so EA should be 1. Then next 2 bits, they are not used. Then we have the, say, serial, we have to enable serial timer 0 and external 1. So accordingly, this is bit is 1, then these 2 bits are 1, then other bits will make it 0. So we get this 1 0 0 1 0 1 1 0 in binary or 96 in hexadecimal. So when you just load IE with this bit pattern, automatically it will enable the serial timer 0 and external 1 interrupt, and the global EA will also be equal to 1. The same way we can, same thing can be done with the help of this different instruction. Set B IE.7. Now IE.7, that is for EA. So EA is equal to 1. So global we are making it enable. Then set IE.4, enable serial interrupt. Then set B IE.1, that is for the timer 0 interrupt. And set IE.2, enable external 1 interrupt. So this is how we'll have to do the programming for enabling and disabling of the interrupts. Then B part, disable or mask timer 0 interrupt. That's what we want to do. So what we can do is clear 1 IE.1. So it will mask the timer 0 interrupt only. Then C part, show how to disable all interrupts with a single instruction. So for disabling with a single instruction, just use the instruction clear IE.7. So that is EA, that is for EA. So EA, if you make it 0, it will disable all the interrupts. So this is how we can do the programming for enabling and disabling the interrupts. Then let us go to the steps in executing an interrupt. The first step is, it finishes the instruction it is executing and saves the address of the next instruction, that is the program counter on the stack, PC on the stack. Then it also saves the current status of all interrupts internally, that is saved internally. Then it jumps to a fixed location in memory called the interrupt vector table. We have already seen the interrupt vector table that holds the address of the ISR. Depending on the type of interrupt, it will go to the particular location. Then next step is, the microcontroller gets the address of ISR from the interrupt vector table and jumps to it. It starts to execute the interrupt service routine until it reaches the last instruction of the subroutine, which is RETI, that is return from interrupt. Then upon executing the RETI instruction, the microcontroller returns to the place where it was interrupted. So these are the general steps for executing an interrupt. We'll see the timing, how the interrupt is executed, execution of. So here we have the main program execution without interrupt. So as the time goes, it will always execute the main program. Then here this is program execution with interrupt. So here we have the main program. So as soon as we get the interrupt, we will go to the interrupt service routine, and when it is completed, it will return back to the main program and it will execute the main program. Then again, when it receives the interrupt, it will go to the interrupt service routine. When it is completed, it will return back to the main program and again execute the main program. Then whenever again it is interrupted, you will go to the ISR, interrupt service routine, and again it will return to the main program. So this is how the execution will take place for the interrupts. So with this we come to the end of this video. If you like the video, press the like button, share with your friends, and subscribe to our channel Engineering and Technology for You. And if you want to get notifications, press the bell icon. Then if you have any questions or queries, you can contact me on Facebook, Twitter, Gmail or Instagram. Then thanks for watching.